Okay. All right. I'm on a 6. I think I can do better that way. All right. So for the exams, I graded them. I have not graded your other assignments yet. I do apologize for that. I will try to have everything you've done so far back to you by Tuesday. Um, but I did want to get the exams back to you quickly because I know that there was some concerns, things like that. Overall, I think that you guys did all right. The last question, I was not very happy with myself the way I made it. So essentially, the last question, I didn't take off points for anybody, and if it looked like you'd spent a lot of time and gave a lot of thought into it and put a lot of effort into it that made sense to me, then I probably awarded some bonus points. If it also looked kind of like you had maybe not spent enough time somewhere else because you had put your time there instead. So I hope that helps make it fair by doing that, or more fair rather. So I'll explain when we get there why it was a problem, and kind of what my thoughts are for that. All right, so then just kind of want to go through it. If we have extra time, we'll probably start a little bit on disinfection, although I didn't. Not sure we'll quite get there. Okay, so for problem 1, we have a graph here. It's asking us what type of reactor would produce this result given that it's a pulse input tracer test. Is that reactor ideal? And then to draw a plot that would depict a short-circuiting event. So if we consider a pulse input, and kind of in our 2 flow-through reactors that we would use a tracer test would be, we could have a CSTR that's continuously stirred, have flow going in and flow going out. And I'm just drawing the reactors here, not a tracer test diagram. We could also consider a reactor that kind of looked more like a pipe, where we had water flowing through, like that. And so if you consider what a tracer test would do if you put a pulse into it, and you're measuring continuously on the output, so you're measuring here or here, and you put in a pulse, if it's ideal, then when you put a pulse in here, it's immediately going to be mixed throughout the whole thing, right? If you put a pulse in here, it's immediately going to be mixed within this plug, and then that plug will travel all the way through and then come out. And so what you would see is after some time, you'll get a peak for the plug flow. You'd have just whenever you reach your hydraulic residence time, you'll have one big plug. Let's see if that's 1 hour, it'll just come out all right then. Okay, so you'll have the highest peak there. Whereas a CSTR, if it's ideal, it will start kind of at the whatever is the highest concentration and immediately be going down. So this plot looks similar to an ideal CSTR, but since it's not immediately mixed, then we don't have the high concentration start like right here, because it would just look more like that if it was perfectly mixed. So this would be CSTR and not quite ideal. And so then if you were to consider what a short-circuiting event would look like, that would entail that in your CSTR, normally it all gets mixed throughout the whole thing. In this case, we have some stream of water that's kind of going directly from one end to the other. Now, it doesn't really matter what that looks like in the reactor itself. It just means that rather than getting perfectly mixed, some of it is escaping before before the rest of the tracer. And it's the current drawing looks more like it's well mixed, but not perfectly instantaneously mixed, right? And so if you were to draw something that had some short circuiting, you'd probably have kind of the similar effect if it was the same reactor but it started short circuiting, you'd end up having kind of a similar effect, but then you'd probably have a higher initial and then it would drop down lower, something like that. And maybe some volume is not being mixed at all, or less mixed because that part of that volume is going through faster. So you'd have something that was shaped a little differently, and that's kind of what I was looking for, is like some of it's coming out too early, and then consequently perhaps some of it's not making it out quite as fast. And you know, this is drawn kind of poorly. Obviously it's not going to increase, but it's not likely to. So something along those lines is kind of what I was looking for. I wasn't too concerned if it looked something along those lines. Yeah. Yeah. Go for it. Yeah. Yeah, I've got the grades recorded. So, and if you have any issues or anything with it, we can talk about that. But yeah, they're yours.
I've already written on it.
Oh, well, I needed yours back.
Oh.
I don't trust you. Okay. So for this, the second one here, question 2, we said, draw and label generic curves for 0 order, 1st order, and 2nd order decay reactions on the space provided. And so we had y and x axes labels as concentration and time. I think there was one person who subdivided this and changed the y-axis so that each one was a linear drawing, and that was not quite what I intended, but it was okay. It was clear that you knew the content here. So what I was looking for is a linear decay. If we just started at the top, this would look, you know, like some straight line down, kind of like that. A 1st order decay would be more like that, and a 0 order decay, since it's dependent twice on the concentration, you get really rapid decay when you have a lot of this stuff. So it's a very steep, and then eventually it really tapers off. So it's kind of like a 1st order, just more extreme in a way. And if you take a look at just plotting different lines from algebra or whatnot, you might associate that, and especially when we answer this other question, you know, the linear is pretty obvious, but the 1st order is like a log plot or an exponential that has a you know, a negative exponent. The 2nd order is more like 1 over x type of thing. So so A asked what y-axis label would linearize the 1st order. That would be log or natural log of your concentration. Either one will work. So either one was fine. And then the easy way to do the 2nd order would be 1 over c. And if you were to take a look at the last page, I did provide you the integral form of the 2nd order, or the integration for the 2nd order rate equation there for a batch system, where we have the integral of dc over c squared from c naught to c is 1 over c minus 1 over c naught. So could have, if you noticed that, you probably could have made use of that to kind of consider that. All right, any questions or issues? Problem 3, I was fairly lenient on again because we really didn't talk about it a lot. This is just kind of a concept question about the sedimentation and I guess the different classifications of sedimentation occurring. And so it starts off mentioning there's a few different classifications, 1, 2, 3, all the way up to 5, I believe. And so answer the following questions regarding those. And part A said describe at least 2 fundamental assumptions that differentiate these types. And so there's a few things that a few answers that are that were fine. And as I'm reading this right now, I realize that while I was grading, I was thinking about type 1 versus type 2. So if you had an answer that had relevance to the other types, and you feel like you deserve credit, let me know if I took credit away. But some things that were, and that was because the next question goes to type 1 and 2. But the question itself asks the just fundamental assumption. So it could have been anything like the settling velocity of particles, whether that's constant or not. Whether or not you had discrete particles, whether flocculation was occurring during the process or not, and those are all kind of dealing with 1 and 2 primarily. But if you go up to 3 and 4, there's like hindered sedimentation because there's just so many particles and they're starting to hinder each other. You'd have that blanket formation. Yeah, and that hindered, that's kind of deals with compressibility of the network of particles. Okay, so anything of those sorts would have been fine. So double check that there wasn't something that you felt like needs credit that I took a point off on or something. But generally, I didn't take much off anyway. So then the part B asks if a sedimentation basin is designed with type 1 sedimentation in mind. But then a study showed that they're actually settling according to type 2. Should the operators be concerned about incomplete settling? Why or why not? And so the real difference between type 1 and type 2 is whether or not we can use the Stokes equation in some sense. So I guess we could kind of write that here too. But the Stokes equation was the one that let us use a Vs that was constant because we had discrete particles with no flocculation occurring. So type 1 was Vs was constant. We were able to use the Stokes law to derive that equation for sedimentation, and no flocculation. And then type 2 was essentially flocculation was occurring. So particles are sticking together. Vs is not constant. So my conclusion then, given those facts, were that, if we're not provided any other information, then we'd be assuming that the particle's size was increasing, given that they are flocculating, and that would mean the settling velocity would increase as well. And so presumably, Vs would be increasing if anything. And so we probably don't need to worry because they'll be settling faster or better. Now, if we ended up finding that type 3, 4, 5, or whatever sedimentation was also applying, then maybe something else would become important and we'd have to be concerned. But given that it was just type 2, that meant not concerned. But again, I was sympathetic if you based on the assumptions that you listed or made, if you made some rational argument, I probably didn't take much off if you had the wrong answer. Okay, part 4, or problem 4 was essentially a ionic strength equation, just kind of talking about, or problem, talking about looking at how to know how destabilized a solution is going to be given 4.5 grams per liter of sodium bromide versus 250 milligrams per liter of alum, or aluminum sulfate. And so I asked you to tell me which one was more likely to induce destabilization and provide a quantitative answer. And so really I was looking for you to solve for the ionic strength of each one. Yeah.
No, I'm just
Okay. Not allowed. So in order to give a quantitative answer, this is what I was expecting. So in order to find these, we'd need the molecular weight, all of those things. Just gonna breeze through it because I trust you're all able to do this. Gonna just write these up real quick. So for sodium bromide, this was 102.5 grams per liter. For the alum, it's 341.37. Sorry, grams per mole, not liter. When we solve for how many moles per liter of sodium bromide we had, we can say 4.5 grams per liter times 1 mole for every 102 grams. This is going to get us 0.044 moles per liter. And when we plug in the ionic strength equation, because they both have one charge, it's 1/2 times 0.044 plus 0.044, and it just equals 0.044 as our ionic strength. We can do alum likewise. Here, I'm just going to kind of shortcut a little bit. We have 0.25 grams per liter. We can multiply that by our 1 mole of alum per 341 grams of alum. This gives us 7.32 times 10 to the minus 4th moles of alum added per liter. And then if we go and take that, do the molar conversions, or do the stoichiometry, we will find that our values here, the alum should be 0.001465 moles per liter. And our sulfate should be 0.002197. Okay, so there's the values we would use to put into our ionic strength equation, and I'll spare you those details and say When you do that, this should be 0.011 moles per liter. So that means our ionic strength for the sodium bromide was greater than the ionic strength for the alum. But it wasn't too far off. So we see that, if we increase that alum by a little bit from 250 milligrams per liter to maybe half a gram per liter or something, we could start getting competitive with that sodium bromide at 4.5 grams per liter. So just a little exercise, ionic strength, hopefully pretty straightforward, and just remember that we define the ionic strength as the sum of our concentrations times their given charges squared. You have that equation. All right. So unless there's any issues there, we'll move on. Problem 5 was a flocculation problem. We have the Mississippi nearing the Gulf. Not a particularly realistic setup here, although I tried. We've got brackish water forming, and as it's mixing with that saltier water, that salt water is causing some destabilization, and a bend in the river is acting like a flocculation basin. We've got a volume. We're assuming it's well mixed. Again, not very realistic. The water is 25 degrees Celsius. Mixing intensity in the basin is 150 per second. And just also not very realistic. If the flow into the river bend is that large number, and the influent water contains 5.5 times 10 to the 8 particles per milliliter, they're all 5.5 micrometers in diameter. And each of the aggregates leaving the basin comprise 17 of the initial ones. Question ultimately is, what is the collision efficiency of the particles? So we're looking for this guy. So our collision efficiency, that goes into our equation for K, where we have this collision efficiency times 4 times our flock volume times G, all that divided by pi. So we're going to need to find K and solve for this collision efficiency given that setup. In order to find K, we need to know what our mass balance looks like for the system and relate that to the outcome that we were told. So when we were told that the aggregates leaving the basin each comprise 17 of the initial particles, what we're saying is for the number of initials per each of the final particles, that ratio is equal to 17. So that was one of the key components here to see where this mass balance was going. And then we just need a mass balance equation to get some relationship of this given the system. So basically the information, we've got a flow, we assumed it's well mixed, we're dealing with a CSDR here. So in that case, and we can assume it's at steady state, this is going to be Q n naught minus what's going out, Qn, plus that reaction where we have in that volume, we have our K times N. Actually, this is a decay reaction because we're merging particles, reducing the number. Okay, so this is our kind of generic baseline mass balance here. We can simplify and say that's 0 equals n naught minus n. So I'm just dividing everything by Q here. Minus tau K n. So tau being our hydraulic resonance time. And then ultimately simplify that. If we divide everything by n, we can end up with n naught over n, and move the other stuff to the other side, and have 1 plus tau k. So relatively simple equation to work with to solve for k from here. And I guess you could go ahead and take it further to solve for that. But what I wanted to show you, this is, now we can equate that 17 equals 1 plus tau k. We can solve for tau, and so it's going to be tau k equals 16. Or k equals 16 divided by our hydraulic resonance time. So then we can take it back. And we still need to solve for the for G. Well, G was given, but the flock volume, right? So the flock volume was something we need. G was given as 150 per second. So the flock volume then, this is, again, that equation that's kind of telling us, given some volume of water, how much of that volume is actually particles and not water. So this should be a fraction that is less than 1 and greater than 0. So that's one thing you can do. And it also should be unitless, so we need to make sure the units are matching. So this, we have the equation for this. This is going to be essentially the equation of a sphere, the volume of a sphere, pi dp cubed over 6 times the number of those spheres we have per volume. And we're using an initial because that's what we have information on, the diameter of the initial ones. So with that, we need to convert the diameter to meters, and we need to convert this particles per milliliter into particles per cubic meter. So we take this to meters and this to cubic meters, per cubic meters. When we do that, we should be able to end up with a flock volume of 4.79 times 10 to the minus 8. So not a lot of the volume there is actually particles. Okay, with that we can also solve the tau. This is V over Q. Which turns out to be just under 9 seconds. And given all of those pieces, we can say that K is 1.79 per second. And from there, we can finally put in the numbers that we have and solve for our collision efficiency, and that is 0.196 as our final answer. So any questions or issues with that? So the next problem kind of built on that same one, but I gave you some new values, so we didn't have to, hopefully didn't have to get the previous problem correct to get this one. And here we have that same water flowing out into the Gulf, and essentially we are getting particles that have been destabilized. And now we are assuming each of those particles, those 5.5 micrometer particles, are now comprising aggregates that have 25 particles of the initial particles per every aggregate. Okay, then we have the density, the water temperature, all of that. And so the first question is, what is the diameter of these new aggregates? So diameter of an aggregate. And we're told that each of the aggregates has 25 of the initial ones. So we know that what doesn't change is the volume, right? So we have these little spheres, in some amount of volume here. We have 25 of these spheres initially, and I'm not going to draw all 25. And then in the volume, we have one particle that's made up of that same number of spheres. It's not going to be perfectly spherical necessarily, even if we end up assuming that, but it's going to be some aggregate that has the same volume as 25 of those ones, right? We don't know exactly the diameter yet, but we do know that the volume of these guys is going to be equal to the same volume, right? The flock volume stays the same. So the volume of let's say 25 times the volume of one of the initial particles is equal to the volume of one aggregate, right? That part we know. So that's the relationship that we're going to use here. And so we can say that if we do make the assumption that this is spherical, then we can say the volume of an aggregate is going to be equal to 25 times the volume of one of those particles, which is pi times diameter of the particle cubed divided by 6, right? So we know that for the initial particle diameter. With that, then we can also say that our pi times the diameter of an aggregate cubed over 6 is equal to all of that, right? So 25 times pi dp cubed over 6. So with that, we can end up simplifying a little bit, divide pi from both sides, multiply 6 from both sides, and then get our final relation. It turns out that the diameter of an aggregate then is equal to 16.08 micrometers. Okay. So then part B says, given the flow rate of the river, how far would you expect to find sediment from the mouth of the river? So this, there's a little bit of geometry involved here, because it says in the problem prompt, it discharges into the Gulf, it mixes with seawater, resulting in completely destabilized, and then it acts as a sedimentation basin. And it says, let's imagine the basin area is as a perfect half circle. If I can find my perfect half circle, and the flow from the river discharges with a constant velocity radially from the mouth of the river. And so essentially what we're saying is we have the river flowing along. It meets the ocean or the Gulf, and we're just kind of assuming that this is just a flat meeting spot. And from this point, we have radial flow outwards. Such that we make a perfect half circle. And that area here is going to be what we're interested in for the sedimentation. We can just look at as if we have a circular sedimentation basin, but just going from the half circle there. So that means our area of the basin, instead of pi r squared, it's going to be pi r squared divided by 2. Or we can also say pi diameter squared divided by, instead of 4, this would be divided by 8. Okay. So then what we need to do to relate this distance here to find that radius, and it's probably better just to leave it as the radius because we don't really need the diameter this time. To find that, we know that our, so to speak, design velocity that describes a basin that perfectly removes all of our particles at V naught, we can say that's going to be equal to the flow rate going through that basin divided by the area of the basin. And so with that, we can equate that as well to the settling velocity that these particles will have. And we can then calculate, okay, what is that settling velocity given our equation? So from the Stokes relation, we have this equation. We can use, and we can get a sedimentation velocity for these particular particles to be 5.59 times 10 to the minus fifth meters per second. And I will say that double check that you're doing the units properly, because our mu is in kilograms per meter per second. Our diameter of the particle needs to end up in meters. It's in micrometers, so let's say it's in micrometers, which means it's 5.5 times 10 to the minus 6 meters. And then the densities as well, we want them in kilograms per cubic meter would be generally the most convenient way. I guess you could potentially change everything, but you'd have to include the acceleration due to gravity here. You could potentially change everything to a different unit if you wanted, but I wouldn't necessarily recommend that. Okay, so with that, we can then solve for our radius, because now we have this, we know the flow, we know the sedimentation velocity, and so we can solve for the area. I don't have that written, so we can solve for the area, which we can substitute in for r, and ultimately find our r value to be essentially 13 kilometers, 13.8 kilometers would be the distance there. Now, not a particularly realistic scenario again, but you can imagine taking an approach like that and making it a little more complicated and understanding how our particles are moving in the environment, just kind of as a non-engineered example, taking engineering equations to describe it. All right, any questions or issues here? Okay. All right, so the last problem, again, I mentioned earlier, not particularly happy with the problem itself, and I do apologize for including it. It's interesting to think about, but I did not set you up for success here. So the problem says a manufacturing process requires two different reactions that affect the concentration C of a contaminant byproduct. Both steps are necessary, but the arrangement does not matter. Reactor A is a CSTR and B is a plug flow reactor. In either case, the first reactor will produce the contaminant and the second reactor will remove it. So the question is, what is the optimal order to arrange the reactors to achieve the lowest effluent contaminant concentration at the end of the day? Circle your answer. Assume that growth and decay rate constants are the same magnitude. and I put a note that you don't have to perform calculations, but you are welcome to um, assume some sort of generic values. There is a problem here because there's a couple problems here. First of all, it's going to depend on which rate order you decide to use. So I should have specified that. The second problem is if you're not using zero order and you're not assuming that there's some influent concentration, which I think I didn't mention it as something that's coming into the inflow water, then if you have no starting point with a first or second order rate, you're going to have no growth. And so it's going to be a pointless problem. So if you start thinking about it in those terms and you have first order or second order, if C naught equals 0, then you're going to have 0 throughout the whole thing. Because the growth depends on how much is there to begin with, it's growing, it's like a bank account, right? You're not going to be earning interest on $0, right? It just doesn't work. So that was kind of dumb, right? So this is no different. So that means if you were trying to solve this using first or second order, then you had to assume some sort of C naught. Then I think, depending on the value you have and the value of your Ks, generally, so if C naught is greater than 0, then generally what you're going to see is for that type of reaction, your CSTR is less effective to carry a reaction forward as rapidly. They're pretty good for just knocking out like 50% of the contamination or something like that, a solid chunk. So when we do like wastewater and we have a CSTR that's essentially a waste activated sludge, they do a pretty good job knocking out a large portion of it. But if you really want to get it past the 90%, all the way down to like 99.99 type of thing, that's when we tend to go towards plug flow. So then if C naught was greater than 0, then we usually think, and this might depend a bit on the K values and the C naught value that you use, but I would normally think that the first arrangement would probably be better. But again, you can already see why this was not a very interesting, but not a good question. Now, if you have a 0 order, then another interesting thing happens. Doesn't matter what you're starting with, but if the rates are the same, it actually ends up that it doesn't matter here either, because the reason that a plug flow reactor could be better than a CSTR is because you're dealing with, some high amount. If you're doing a decay, you're not mixing it with the other stuff that's already been degraded, so you have a higher proportion of contaminant being removed over time because it's not mixing with it's not being diluted with stuff that's already had some removed away from it. Whereas the CSTR, as soon as the water enters it, you've dropped down to the 10% of your total or whatever. So the amount, when you do the equation where you have K times C, in this case, you have C naught and C, and the C is the same here. Whereas in the plug flow, you have, you know what, I'll just draw it down here. My cursor will appear again for me. There we go. Down here, you have C naught and C, but right here, you have like C at 1 minute or whatever. And that's a lot higher than the C over here if you're doing a degradation experiment or decay. So that would, would apply up here. At any rate, that's only relevant for a first order or a second order, that phenomenon. So for zero order, it just doesn't matter. They're both the same. Because it's like you're adding 5 units per time. It's like doesn't matter how many units there are. You're just adding 5 per time. You'll get a total of 20 here, and then subtract a total of 20 here, or whatever. It doesn't matter. If they're the same hydraulic resonance time, it's the same. So my hope was that it got you thinking about how you would solve that, thinking about some of these reactor dynamics, and with the grades, I hope that I've helped make it fair, awarding you some points if you gave it some good thought, not taking points away if you realized it was, maybe you didn't recognize how dumb of a question it was, but you recognize your time was better spent elsewhere. So if you have issues, feel that was not the fairest arrangement, let me know, and we'll talk about it. So that was the exam. I'm going to try to, for the final, I will try to make it a little bit closer to the content. I think that I have changed some things since last time I taught the class, especially for the membranes I did a little bit more on. So I'm going to give you a homework on that soon, on the membranes in particular. So we'll have that. Then a little bit later, we'll have a homework on kind of disinfection and advanced oxidation processes. Okay. Any questions or issues, comments, concerns? Okay. All right, well, we have 20 minutes left. I think I'll just leave it here. So I'll plan to have more graded items back to you Tuesday. We will also start our unit on disinfection then as well. All right. So I'll see you guys next week. Have a good weekend.